Now that we derived the conservation of mass equation, now we'll turn to conservation of momentum a second time. We'll look at linear momentum in particular. Remember that the forces acting on a fluid parcel of a continuum are two kinds that will divide them into internal forces and external forces. External forces will be represented by F, which are as a force per unit mass, and it acts on a fluid parcel or element omega. And we'll write this body force this way. So this is like a rho of density times this force integrated over the unit volume or fluid element. The internal or so-called contact forces act on this element volume omega through its surface, which we'll sometimes write as gamma or partial omega. So partial omega represents the surface, and T sub n is the force per unit area, which is exerted by the material on the particular volume outside partial omega. This surface force exerts on the volume omega will be expressed via this integral in equation 141, just like 140. It's very similar, except it's a surface integral denoted by ds and partial omega. The Cauchy principle shows that Tn depends on any particular time and position and the orientation of the surface, ds. Just remember, these fluid parcels are not necessarily little cubes. So Tn is a function of space, time, and the normal direction. Newton's conservation of linear momentum shows that the rate of change in linear momentum of a material volume will equal the resultant forces on the volume, and we'll assume that F is a known quantity and not something we're trying to solve for typically. So we'll say the ordinary derivative of the volume of rho u dx, which represents momentum per unit volume, is equal to the volumetric integral, the body force, plus the surface forces, which we just introduced in 141. So this is 140. Remember, we previously developed the formula for the left-hand side in a very similar fashion, which is the ordinary derivative of the volumetric integral of rho f will be an integral of rho material derivative of f. These two particular equations, 144 and 143, can combine to be 145. The integral volumetric of the density with material derivative of velocity will be the two body forces and surface forces summed. An important factor here is that this vector Tn is normal and can be expressed as a linear function of n in this particular form. So write Tn as the normal vector times capital T, and we'll write T as the so-called stress tensor. So L cubed will be this particular volume of omega. We'll divide both sides of the equation by L squared and let the volume go to 0 to be like a little plane. And we'll write that as in 147. And we'll say that the stress is in local equilibrium. Omega is a domain which contains the fluid, remember, and a rectangular tetrahedron with vertex and arbitrary point, x in partial omega the surface, will have three faces parallel to any particular coordinate plane. So you can imagine a little tetrahedron with three of the faces in the planes of x, y, z, and the fourth face will be connecting the 3 points that are not at the origin. The slated faces will have a normal of n1, n2, n3 vector and have an area of sigma. The normals to the faces will be negative E1, E2, and E3 respectively, with respective areas normals with the surfaces, areas. This particular equation can be applied to families of tetrahedrons by letting sigma go to 0. And we can write 148 and write it the right-hand side to be 0, because the sum should be 0. Now we can write our previous equation using Green's theorem, 149, as the volumetric integral of rho times the material derivative of velocity will be equal to a volumetric integral of rho times the divergence of the stress tensor. We can integrate both sides because it's the same integral with dx, volumetric, and of course, we can just drop the integrals now. Rho of the material derivative of u goes as rho f plus the divergence of t. And we can simplify this as 151, which we find as the Cauchy equation of motion in differential form for I equals 1, 2, 3, which represents perhaps the x, y, and z directions in the Cartesian coordinate frame. And this should be very much starting to look like the Navier-Stokes equations, which we just previously derived in a slightly different way. We still need to formulate T, the stress tensor, and it'll depend on the type of fluid we really care about. The simplest types of models, and ones we usually look at, will involve contact forces that act perpendicular to the surface element. That'll be T goes as negative P, a pressure, times N. P is the internal pressure or static pressure or internal stress of the fluid. The minus sign is chosen so that when P is greater than 0, the forces or contact forces of the fluid element or parcel will be on a closed surface and tend to compress the fluid, which makes sense and is intuitive to us as people. So remember, P represents the pressure exerted from the outside of the surface on any particular fluid, parcel, or element. And all fluids at rest will exhibit this stress, even if they're not moving. That is, remember, a fluid parcel of area always experiences a stress within itself, normal to itself, in every direction. And this stress is independent of any particular rotation. So it's isentropic, excuse me. The fluid in this state we'll call hydrostatic. Now the equation of motion for a perfect fluid can be written as 153 of rho times the part derivative of u with t plus u dot nabla u is rho f minus nabla p. Here we can also write u dot nabla u in a summation form here, if we want to expand it out in Einstein or index notation, which we explained earlier in this class. All real fluids will exert tangential stresses, right? According to viscosity across surface elements when in motion. And that tensor T, of course, will not be diagonal anymore. It's 3 by 3. The stress tensor can always be written in this particular form. We'll write Tij is negative P of delta Ij, where delta Ij is the Kronecker delta function. Remember, if I equals J, it's 1, and if I not equal to J, then it's 0. Plus Pij, which we'll introduce as the viscous stress tensor in this notation here. We'll assume that Tij, that stress tensor, is always symmetric, and you can see really the diagonals involve the pressure plus an extra viscous component. So it's always symmetric in this case. We can then write the Cauchy equation we previously developed using 155 as 156.